The laws of physics do not forbid the possibility of time travel. If you could have a stable wormhole, you could build a time machine. But in some sense, the world around us is an illusion. The particles that make us up, electrons, protons, neutrons, have mass, but that's an illusion. At a fundamental scale, they're actually massless. Mathematics describes the world, and mathematics produces patterns. And if the world is describable by mathematics and the laws of nature are explicable as mathematical laws, then it's not too surprising to find remnants of mathematical truths in what we see in nature. Yeah, it's fascinating that it's fascinating, but not too surprising that different structures are governed by the same mathematical laws. That's one of the wonderful things about physics. So it's not too surprising to see the same representations crop up in many different places. If you didn't believe in God, would you go out and murder someone? And most people, say no. We innately understand some moral basis which allows us to exist more or less peaceably with our environs. And the scientific method is designed to overcome the known fact that humans, including scientists, and scientists are human, have biases.
Welcome back to the Gnostic Informant, and you are about to attain true gnosis. And today I'm joined by Dr. Lawrence Krauss, theoretical physicist who authored or co-authored more than 300 scientific studies and recipient of a bunch of awards, including the Lilienfeld Award, which puts you on a short list of people like Stephen Hawking. So that's pretty impressive.
It's nice to be on a list with Stephen, who was an old friend of mine.
Yeah, great guy.
Anyway, it's nice to be with you virtually.
Yeah, this is great. So just started off, I have a question from Derek Lambert from Myth Vision, and I'm just going to play. He recorded it. I'm just going to play it, and you can just answer that, and we'll just go from there.
Okay. Professor Krauss, Derek Lambert, Myth Vision podcast. I'm the host. I have a question for you. Many people talk about the design of the universe. They look at this universe and they see mathematics, they see structure, and they use that as an argument for a mind or a God or a creator looking at the universe itself. As someone who's a theoretical physicist, in what way does your work potentially help answer this question of, was this really all chance? When it comes to design and fine-tuning, in what way does your work actually come in and kind of debunk the notion that a perfect, all-powerful designer created the world, the universe, everything that we see? Is there a way to answer that question?
Well, that's a good question. In fact, recently I wrote for Inference magazine a long article, along with one for the Globe and Mail in Canada, on how poorly designed the universe is. People look around and they say, wow, the universe, if it had different properties, we wouldn't be around. The same is true for the Earth, and that used to make people think that the Earth was designed for life. But in fact, what we understand after Darwin is that life evolved to fit the circumstances, the environment in which it could evolve in. And so it's not too surprising that life forms on Earth fit perfectly well on the Earth. It's not too surprising that life on Earth it fits, if you wish, with the universe, which if it were any different, life on Earth might not be possible to have arisen. But it doesn't imply design any more than the fitness of life on Earth implies design of life. Natural selection works very well, and I often say it's like remarking on the amazing fact that my feet are exactly long enough to touch the floor. If they were a little shorter, I wouldn't be touching the floor. If they were a little longer, I'd be under the floor. But more than that, if you look at the universe, most of the universe is not well designed for us. Most of it's uninhabitable for beings like us or life forms like those on Earth. And in many ways, the universe is constantly trying to kill us. We're lucky we've survived this long as a species. But even the fundamental parameters that look like they're fine-tuned, and the most famous one, which I discussed about as early as anyone, is the energy of empty space, which seems to have a very peculiar value that we can't understand. And it was pointed out by the late physicist Steven Weinberg that if it were much larger, that value, then galaxies wouldn't have formed and life wouldn't have formed. And some people say, wow, that's evidence that the universe was designed. But on the other hand, it turns out if that weird quantity was zero, which is the value we always thought it would have, which seems natural, more natural in many ways, the universe would actually be more conducive to life. So I guess I like to think of the argument from that Carl Sagan used. It said, if the universe is designed for life, it's an awful waste of space. A pretty big universe, so you could just have this Earth. And the other aspect is, if the universe were different and had different properties, sure, we wouldn't be around. But we can't say that there's no life that'd be around. There could be life of a very different form, and that life could speculate and wonder why that universe was so well designed for it. As I often say, it's like an intelligent fish, wondering why the universe is made of water. And the answer is, well, if it wasn't, the fish wouldn't be around. And so all that even here on Earth, we've discovered what are called extremophiles, life forms that exist in situations we never thought it would be possible for life to exist in. Boiling hot water, acidic environments. And so if that's any guide, it suggests that life in many ways can evolve in many different environments. And if things were very different, then we might find that we wouldn't be here, but maybe we'd be some other sort of intelligent being with very different properties. Clearly, people have it backwards, the same way people before Darwin used to have it for living systems on Earth. The universe wasn't designed for life. Life evolved. Our life, the life we measure here on Earth, evolved because in a form that's consistent with the physical properties of the universe in which it evolved. That's not so surprising. There's no evidence, as far as evidence of purpose or design, as I say, there's nothing that suggests that there's any specific design in our location. It certainly seems to be rather random, and most other locations in the universe, as I say, are not so fortunate. You would have thought that a being that designed a universe for life would make the whole universe hospitable for life in one way or another. And anyway, those are some arguments.
Well, to add to what you just said, that makes a lot of sense too, is so if you're designing life and you have photosynthesis for plants, why can't animals photosynthesize? Why do we have to eat each other? Like, we literally have to eat the faces off other beings to survive. Energy can't sustain energy unless it eats other energy.
Well, I can tell you part of the answer, by the way, because photosynthesis doesn't provide enough energy for a moving animal.
Right.
It's not eating so much as the fact of respiration of oxygen.
Right. But
I'm saying Adam, I write all about that. It was harnessing oxygen that allowed this molecule called ATP to, that you could basically release or produce about 37 times as much energy per unit material as you could otherwise. And until there was enough oxygen in the atmosphere, and life, if you wish, learned how to respire, how to use oxygen. And all oxygen does is take away electrons that dump energy into life and allow it to exist. Until you had that, you had plants and immobile stuff, which was pretty peaceful for a few billion years on Earth. But things got more interesting. And when things get more interesting, it's both good and bad, I suppose.
Yeah, and I mean, obviously, what I said doesn't make sense. But if you're a god that can do anything, you can bypass those laws and just everybody here's
principle. That's why I guess. I mean, if you're a god, you in principle can. No one really defines what God is, but I guess the idea of God is someone who isn't constrained by the laws of nature. And then, if that's the case, why work within the laws of nature?
Right. There, it's just that you're just going in a circle, which brings.
It's the same argument that's given with that God and sort of rationality. If God, if our morality is given by God, then if God said it's okay to murder, would it be okay? If it isn't okay, then
they would say yes.
He's guided by a higher moral purpose. Then why just get rid of the middleman?
Right.
You don't need God anyway.
And speaking of that, real quick, because I was going to get to that, I wanted to have a few steps in between, but just since you mentioned morality, if you look at throughout time, ancient civilizations had these law codes, and they always said these laws are from God, pretty much, almost across the board. You got the Ur-Nammu law code, you got the law code of Hammurabi, and then you got the Bible, you got the Deuteronomy law code, and then you got the New Testament. you can see a progression from going from, okay, we're going to throw you into the lake, and if you survive, you're innocent, to, okay, we're just going to cut your hand off if you steal. And then to, like, let's be fair. Let's eye for an eye, tooth for a tooth. And then finally, it's like, well, love your neighbor. Okay.
But it's interesting that religion that had love thy neighbor had a different version of throwing you in the lake when they were talking about witches, which was to throw them in. And if they didn't survive, they were innocent. If they survived, they were guilty. It was a much more efficient way of dealing with people
right.
you want to get rid of.
Which tells you that morality comes from, well, I don't know if this is what you think, but I think it's from our experiences.
I think it's a number of things. I think there's an evolutionary basis. I think it comes from a rational understanding of the world and the way it can work most efficiently. So I think, there's a famous saying from Hume, I think, which is you can't get an ought from an is. But I think with an is combined with rational thinking leads to oughts pretty darn close in any case. And so I think, it's look, you can simply ask people, and I've done this in public, if you didn't believe in God, would you go out and murder someone? And most people, say no. Every now and then there's someone who says yes.
Right.
But obviously we're driven by things that have nothing to do with that belief in God. We innately understand some moral basis which allows us to exist more or less peaceably with our environs, and those things arise out of a tribal culture, and they get codified often in a religious jargon because that helps keep the tribes together. But when you think about it, it's just a way of enforcing adherence to a set of rules that make sense for the most part. And they don't always make sense either, of course. That's the whole point. I mean, the Bible is full of rules that are rather horrible, but most people ignore those and just take the ones they like.
Yeah, and I'm actually having somebody on after you who we're going to talk about the history of science. And I would argue that, like, you hear all the time from like people like Jordan Peterson, they'll say, Western civilization would be nothing without the church and Christianity. But it's like, wait a second here. If you go back before the church, you got the Epicureans, you got Democritus, who was talking about atoms. They were onto stuff. And then the church came along, and then it's like they went backwards for 1,000 years. I would argue the opposite.
Well, I think there's a little bit of both. That's the point. It's as usually the case. Sort of extremes or stereotypes are usually just that. And so it's true that the enforcing adherence to religious doctrine by the church held Western civilization back in the early Middle Ages. At the same time, it's also true that the repositories of books and learning were religious groups, monks, and later on universities. And so, the kind of intellectual climate that involves thinking, reading, writing, and did grow out of the church later on. And of course, eventually those universities grew out of the church. All the early universities were church run. Eventually they grew out of it. So there's a give and take. Certainly the existence of Western universities goes back to church run things, but the existence of ignorance for a few hundred years was among the masses of the public was also due to church run hierarchy. So it's a combination of good and bad, I think.
And if I'm not mistaken, wasn't it a Jesuit who discovered the Big Bang or theorized it?
Yeah, Lemaitre was a Belgian priest, Jesuit priest, but he was also a physicist. He did his PhD at MIT,
right?
And he was the first one to recognize that the solution of Einstein's equations implied basically that you had an expanding universe that arose from an initial point. And he discovered that he wrote that down around 1928 or 29, which is before Hubble empirically discovered that the universe was expanding. And certainly Einstein didn't buy into it, and Hubble never bought into it. But eventually people realized that Lemaitre was right. Yeah. When he did, by the way, the Pope sometime later said, "Hey, this is evidence of Genesis of the," and Lemaitre, who was both a priest and a scientist, said, "No, stop it. This is scientific theory. You can take it to validate what you want, or you can take it to validate something else. But it shouldn't be taken inappropriately.
And that's fascinating. So I've heard you say, I don't know where, I can't remember where I heard you say this. You were talking, it was on some podcast where you said that the universe at one point was the size of an atom.
Yeah, one of my books called Atom begins at a time when our visible universe was the size of an atom. It was smaller than that at earlier times. But before that, sort of the laws of physics as we understand them break down, so we can't extrapolate backwards with authority in any way. But back to the time when the universe was the size of an atom or so, the laws of physics as we know them allow us to extrapolate back. And it is really amazing. I mean, it's unfathomable to think of all of the energy and matter that's now in the universe in one way or another existing in a region that small. It's just unfathomable. But that's the great thing about the universe and science, is it forces you to stretch what you can imagine.
So to go back a little bit, because you said that when you look around, you don't see anything that points to a designer. However,
in fact, if you ask me, I see all evidence to the contrary.
Sure.
We're not designed very well. If we were, we wouldn't have blind spots. We wouldn't breathe out of the same orifice. We ate all sorts of things that if I were going to design a human being, I might design differently. But the universe in general, it seems completely random. And when you look at it, it's more or less structureless on large scales. And the fluctuations from the Big Bang are what are called Gaussian random fluctuations, which are understandable from quantum mechanics, but don't give any evidence of any initial purpose or design.
Now, I agree with that, but I'm going to play devil's advocate for a second. There's this big, there's in math, there's the Fibonacci sequence, the golden ratio, and the New Age movement loves to point to this and say, look, it's everywhere. It's in plants. It's everywhere. Look, there's God's fingerprint right there. How can you deny it? That's what they'll say.
Mathematics describes the world, and mathematics produces patterns. And if the world is describable by mathematics and the laws of nature are explicable as mathematical laws, then it's not too surprising to find remnants of mathematical truths in what we see in nature. I mean, you could just look. The number 2 is profoundly important, and it exists throughout nature. But people don't seem to find that as surprising. But binary aspects of the world are all around us, and so it's fascinating that it's fascinating, but not too surprising that different structures are governed by the same mathematical laws. That's one of the wonderful things about physics. So it's not too surprising to see the same representations crop up in many different places, from galaxies down to living things.
Do you think that might be the cause of it? Is the shape of our galaxy, the energy behind our galaxy having that shape, sort of like down?
I mean, it turns out, speaking of design and not design, if you take a gas of particles, relatively uniform spherical gas of particles, and have it collapse, if they have interactions like our matter does, that will then collapse down into a pancake, and if it has angular momentum, it'll produce a disc-shaped galaxy. So there's nothing. It's beautiful to look at, but if you on a computer just put gravity in and allow particles to collapse, you'll get that structure. So it doesn't require any magic finger to be making it. I mean, snowflakes are beautiful, right? And they look like Christmas ornaments. But all you need are the laws of electromagnetism and polar molecules, and boom, you create snowflakes.
Yeah, I think it's more of like, in hindsight, looking back and saying, look, everything looks like this, therefore it was created that way.
Yeah, I mean, but again, it's putting the cart before the horse. I would have used another way of saying it, perhaps otherwise, but it's putting the cart before the horse. It's saying, hey, these structures are similar, therefore there must be design. But the other thing you can say is, hey, these structures are similar and there's simple laws that always produce those structures. Hey, it demonstrates that the simple laws govern nature.
Yeah. Boom. So now I want to talk about, I don't know how much you know or don't know about this, is the simulation hypothesis.
Okay, I know.
Tossed around a lot. Is there anything to this? Like, is there any credibility?
I think it's kind of vacuous to me. First of all, I see no evidence of it. Usually in simulations, there are bits or pixels that don't work, And you know, and they'd be manifest here as little regions where the laws seem to break down around us, or the laws of physics. You know, and except maybe in Donald Trump's head, the rest of the world works in pretty well ways. And so, and that's the first thing. The second thing is it begs the really big question. Okay, so we're a simulation. Did the beings who created the simulation, are they a simulation? Because they must be more complex than us, right? So are they a simulation? And if they're not a simulation, they evolved from laws of physics that allow them to fall. So it doesn't resolve any questions. It's like turtles all the way down. Moreover, as a physicist, in some ways, it doesn't matter to me, because my interest is in discovering the laws that govern the world in which we live, and that's and you know, if it's a fake world, you know, that's irrelevant in some sense to being a physicist. You know, finding some irregularities that might point out that it's a fake world would be interesting, but there is no such evidence of that. So I don't see that the simulation hypothesis adds anything, nor do I see any evidence of it. It's not impossible, but it doesn't add anything. It doesn't add anything that I can think of. It doesn't answer any questions. It doesn't make things simpler to understand, because once again, it's just like God. You have a God. Well, who created that God? Okay, and again, simulation. So we're a simulation. Are the people who created the simulation also a simulation? Is the simulations all the way down?
It's an infinite simulation.
Yeah.
So, and then that's funny because you bring that up. It reminds me of like the deism, the deist arguments. And a lot of times fundamentalists will hide behind those arguments like, oh, look, you know, it's possible. You don't know what happened before the Big Bang. Therefore, and they'll jump all the way to
let me repeat what I often say, and you've heard me say it before, which is that lack of understanding is not evidence for God. It's evidence of lack of understanding.
Exactly.
Let's make that quite clear. And it invites us to try and understand. And that's the reason I became a scientist.
Yeah. And it's been, if you look at the history of how the goalpost has been being moved, from geocentrism to like it was the church that fought that. It's like, no, the sun, we don't revolve around the sun. We're the center of everything. And then
they fought it, although they probably knew it was untrue, but they fought it because they had good observatories. So
yeah,
they probably were the only ones to know it wasn't true.
Yeah, there's actually some evidence to show that there's people who thought that the sun was the center of the earth or center of the universe long before that was established by, you know, whatever, by just.
Oh yeah, there was evidence of that, and the church, as I say, had good observatories. They probably some of them, other than Galileo, probably had suspicion, or Copernicus. But the history, and I've written about this years and years ago, but the history of science or the history of humanity is to remove us ever further from the center. Ever further, we thought we were the center of the solar system. We're not, but the sun's not the center of the universe. It's not. It's just at a random suburban neighborhood of our galaxy. But our galaxy isn't the center of the universe. It's in a cluster of galaxies, and it's orbiting around a rather dense cluster, and that dense part of our cluster is not the center of the universe. So we keep getting moved more and more away from the center of the universe, and then in other ways we're being removed from the center of the universe. We've discovered that the matter that makes you and I up is just a small fraction of what's really out there in the universe. So we're kind of we get more and more irrelevant the more we study the universe, and that's good. That's fine. That shouldn't make us upset. It should make our existence more marvelous, not less marvelous.
Right. And so that's what I've noticed is that when I look at history and look at like what we know, everything we don't know is where the theist arguments try to dominate.
A lot of the gaps you're talking about. Yeah,
exactly. And that's really what it is. Like, just because you don't know something doesn't mean therefore the Quran is true or therefore the New Testament.
Exactly. I know that's
there to there.
That's why I made that statement. It's really not understanding anything. It does not represent anything about what you don't understand.
I think Neil deGrasse Tyson's right when he says that when we try to fill in the gaps, because I used to be like, well, what's the harm in filling in the gaps with our own beliefs? Whatever. It just feels good. But he made a good point where he said it gets us to stop thinking about these things and we stop trying to discover more.
Well, there's two things. That's one of the points. God is a convenient way to stop thinking, right? I mean, if there ever comes a perplexing question, you say God did it, and that's the same as saying stop thinking, or as Ricky Gervais would go, it's like doing that. But But it's also got another unfortunate consequence, which is that if you believe things that are not the case, that don't support the evidence of reality, then you're likely to make decisions based on those beliefs, which are poor decisions. And and so it leads to actions which are often contrary to the best interests of yourself and other people. It leads you to believe that homosexuality is a sin or something like that, and and um, and so that's the other negative side effect. The first one, that it stops inquiry, and the second, that it can cause reasonable people to do unreasonable things. The late Steve Weinberg, again, that Nobel Prize winning physicist, used to say, and I paraphrase him because I can never get it exactly right. He more or less used to say, there's good people and bad people. Good people do good things, bad people do bad things. When good people do bad things, it's religion.
Wow, that's a good point. And another I was thinking about while you were saying that is that when you start with a worldview that's based on religion, you have to find whatever evidence you get and sort of make it malleable and make it fit that. You can't be like in the scientific method, you can't have a bias at all. But
Well, you can. The point is, no, look, let's make it quite clear. Scientists have biases, but the scientific method, as you point out, the process of doing science, is designed to catch those biases. It's designed based on the fact that it knows its individual scientists have biases. So the methodology works recognizing that, to catch those biases and overcome them, but as a group structure, to recognize that your results have to be tested by others, and your biases can be checked, and so the whole social or sociological process of science and the scientific method is designed to overcome the known fact that humans, including scientists, and scientists are human, have biases.
that's a good point. Now I want to get to a fun one.
Okay.
This is actually a Christian friend of mine who I grew up with. I was talking to, this was a couple months ago, and we're talking about science, and he said, "Well, what about quantum entanglement?" He said,
What about
"Quantum entanglement means that there could be you could be quantumly entangled with the creator right now, and he's watching everything you're doing."
Well, yeah, but people like to throw out these terms from physics, and it sort of upsets me. I'm just fixing my camera. I'm sorry. Um, because they don't understand what they're talking about. And quantum physics, people love to bandy terms of quantum physics around. But quantum entanglement, which is a central property of quantum mechanics, it means that there are correlations between. I'm going to try and get the focus of this better.
Sure.
It means that there are correlations between separate objects, which are not really separate because they're have sort of part of a single wave function. But those quantum correlations get destroyed very easily by interactions, which is why you and I behave classically, and we don't have the characteristics that an electron has in an atom. And so quantum entanglement is incredibly easily destroyed, and physicists are trying to create systems where quantum entanglement can exist over macroscopic scales, and they have to be very, very, very clever to be able to do that in either or cool systems down or isolate them very carefully. So random objects are not quantumly entangled with the world around them in that sense, and they're quite classical because those quantum correlations get destroyed.
That's the thing about quantum mechanics, is it's so hard. It's so like bizarre, I guess you would say, that and not the average person doesn't understand it so much.
Well, I mean, none of us understand that. I'm sorry, this camera.
It's okay. It's not
Out of focus. There we go.
There we go. Now it looks good.
Feynman, who understood quantum mechanics as well as everyone else, said no one understands quantum mechanics. That's because we are classical beings and our intuition is classical, and quantum mechanical laws violate that classical intuition, and therefore we don't have an innate understanding of quantum mechanics. We can understand the mathematics of quantum mechanics and make predictions and build devices like the devices that's powering my computer and yours, and pretty well almost everything in your room is based on quantum mechanics. So we can work with it very effectively, but the sort of the properties of quantum mechanics cannot be expressed easily in terms of the classical concepts, which we innately understand because we're classical beings.
Yeah, and it seems like because it's one of those things that because people don't understand it, they just can apply it to just make it woo woo this,
That's
woo
the
woo that.
secret. And yeah, I know, and it's really abused more than any other area of physics, and it upsets me, but I try to get over it.
So, speaking of like quantum entanglement and stuff that's really really bizarre, you they talk about atoms popping in and out of existence. How does that happen? Can you
It
kind of take us
happens.
through that?
It's quantum mechanics. Um, I mean, particles can pop in and out of existence because quantum mechanics on small scales allows fluctuations. The Heisenberg uncertainty principle means that basically on small enough scales over small enough times, more or less anything goes. If you can't measure what's happening there, then all sorts of things can be happening, and not only can they be happening, they can all be happening at the same time. So it's really crazy.
So
But
that means
the fact that we can't see them doesn't make them imaginary anymore, like God. It because unlike God, there we can make predictions of these particles which we can't see that are popping in and out of existence affect directly the property of things like atoms in a calculable way. And when we calculate based on their existence, we come if we don't include them, we get the wrong answers for the structure of atoms. When we include them, we get the right answers, but not just the right answers to 14 decimal places, the best predictions in all of physics. So we know they're there.
yeah, and so when people who aren't educated with a religious agenda hear things like that, when they hear scientists, when they hear PhD scientists say atoms can pop in and out of existence, they're going to say, "Well, there you go. Ghosts can, and angels and demons can
Yeah,
pop in
well,
and out.
I
It's
mean, look,
proven by science."
people who really want to believe are going to want to believe whatever no matter what you say. Most people, I'm not. Some people, many people can confront their own misconceptions and thereby learn something. That's what we call learning. But some people are so committed to their ideological stances, whether they're religious or whether they're woke, that no matter what the reality of existence is, you can't convince them otherwise.
Yeah, and another strange experiment, I should say, is this split hole experiment, where I think it was misunderstood in the beginning and then sort of got figured out over time. I don't know if you want to take us through what happened with that.
Well, I mean, the two-slit experiment, is that what you mean?
Yeah.
Yeah, no. Well, I mean, I don't know if it's misunderstood, but it's a beautiful demonstration of quantum mechanics. So of the fact that particles are wave-like, like electrons. You know, if I take a wall and I cut two slits in it, and I have a machine gun, and I just keep shooting back and forth. If I look behind the wall, I'll see two spots where there are a lot of bullets right behind the slits. But if I take a wave like light or sound or water, in fact, I was just looking at my dock back there and I saw a perfect example of this phenomena. If you have a wave going through two slits, there'll be what's called an interference pattern, and there'll be all sorts of light and dark spots, or in case of waves, spots with a lot of waving and spots that are completely calm. And so the idea was, well, let's test and see if electrons are particles or waves. So take take electrons and you throw them at these slits, and then you look at the pattern that comes out, and it's wave-like. It's got interference patterns. And you say, oh, well, that's crazy, because the particle went through one slit or another, it didn't go through both. And so you actually have to shine a light or an electron detector if you want, and it then detects each electron going through one slit or another. But when you do that, lo and behold, you look behind the slits, and the pattern is different than it was before. It's now that of bullets. So in the process of observing the electrons to see which slit it went to, you change the pattern. If you don't observe, then the electrons literally go through both slits at the same time and interfere with themselves.
So am I here? Am I hearing you right? You're saying our observing the demonstration actually affects what happens?
Yeah, that's a property of quantum mechanics.
That is
Observation affects the end result, or can affect the end result. Doesn't always, but it can.
so okay. So everything's waves, basically, right?
And particles.
And particles. And when they go through these holes, they
The electron is not localized. The electron, if you're not looking at it, is in many places at once. If you
wow.
measure it, it'll always be in one place. But if you don't measure it, until you measure it, it's in many different places at the same time, doing many different things.
And then
And
can't
the probability that you'll find it in any of those places is determined precisely and accurately by quantum mechanics. Quantum mechanics gives you the rules to determine the probability that electron, which is in many places at the same time, when you actually measure it, the probability you'll find it in this place versus that place, that can be determined exactly using the laws of quantum mechanics.
Wow, it's so bad. And then so people, like I said, like I'm always going to go back to this because this is sort of the whole point. People with uneducated with a religious agenda will hear that and say, well, look, if everything's wavicles, what is a word? A word is a vibration. It's God's word. Oh, look, we're all God's word. So you get those. It's very malleable when it comes to trying to fit quantum science because it's so out of the. It's so different from classical mechanics.
It is. It is. It's as different as can be, but any of the laws of physics can be distorted by people to suggest that God exists if they want it hard enough.
Yeah, I guess that's true. And does this have anything to do with the Schrodinger's cat experiment?
Well, the Schrodinger's cat experiment is the extreme of this, and because it seems so crazy, which is you put a cat. I mean, with an electron, if you're not measuring it, you can't say what state it's in. It's what's called a superposition of states, and if you have a cat in the box, it could be live or dead. And if you and there could have been a radioactive decay that produced a bomb that killed the cat, but that's probabilistic. Until you look in, you don't know. So, but if you look in, the cat is either alive or dead. But before you look in, you could say quantum mechanically the cat is in a superposition of a live cat and a dead cat, and then you determine which one when you see it. But that's the extreme version because you're taking a system in which quantum correlations are well, you're correlating a big macroscopic system to the decay of a radioactive atom, which is the radioactive atom is governed by behaves explicitly by the laws of quantum mechanics, and you're making what seems to be a contradiction. But if you think through it carefully, the quantum correlations are such that you never that instantaneously, effectively, the cat is always either in a live state or a dead state. It's never in a superposition that can be distinguished as such.
So do you think that it's just the observation is just based on, I mean, I'm trying, how do you put it? It's like based on hindsight, kind of like you're just looking back at what there's only two possibilities. You're just looking back.
You're applying the laws of quantum mechanics to a macroscopic system.
Right.
And macroscopic systems, there's ones in which those quantum correlations, which produce those weird behaviors, get washed out very quickly. So basically what happens is that classical systems can be in a superposition, but very quickly they're either in one state or another. And that's why I'm in this room and I'm not outside the room at the same time, because I'm very quickly, any kind of quantum correlations that might have caused, given that kind of strange behavior is washed out so quickly that I behave like a billiard ball.
Yeah.
Now, like an electron.
We're talking subatomic levels here. How is there a way you can describe how small this actually is that we're talking? Can you put it in context, basically?
Well, the great thing is that experimental physicists are now creating macroscopic systems where the weird properties of quantum mechanics are manifest. The simplest one was created in 1911 without knowing it had anything to do with quantum mechanics, and that's superconductivity. If you cool something like mercury down to a temperature a few degrees above absolute zero, suddenly all electric resistance disappears. Not gets small, but disappears completely. And if you hook it up to a battery and you get a current flowing and you disconnect the battery, the current will flow forever without resistance. Superconductivity is an amazing phenomenon. We use it all the time nowadays. But and people are searching for what are called high temperature superconductors, where you don't have to cool them down so low to get that weird behavior. But that property is a macroscopic manifestation of laws of quantum mechanics. And you couldn't understand it without quantum mechanics.
So now let's change it up a little bit. There's CERN is colliding particles. What are they trying to do there? What exactly is the end game here with this?
The idea is to build up higher and higher energies, because the higher energy you have, the better microscope you have, because of the laws of quantum mechanics. So we're trying to basically probe the fundamental structure of matter, and by bombarding, say, protons with higher and higher energy projectiles, what one can explore, in some sense, the inner structure of the proton, and look for new particles and forces, which might help us understand why the forces of nature are what they are and why matter is what it is.
Is this how they figured out about this Higgs boson?
Yeah.
So,
It's because if you smash the particles with enough energy, you can create elementary particles that you wouldn't see otherwise, including the Higgs boson.
and what exactly does that tell us about the universe?
Well, that tells us. I wrote a whole book about it called "The Greatest Story Ever Told So Far." But it tells us that in some sense the world around us is an illusion. At a fundamental level, I know, and that'll make the religious people happy.
It's a simulation.
No, it's not a simulation, but it's an illusion. It's of a different sort. I keep going out of focus. I don't know if the camera doesn't like what I'm saying, but the particles that make us up, electrons, protons, neutrons, have mass, but that's an illusion. At a fundamental scale, they're actually massless. But because it turns out in the early history of the universe, this Higgs field formed throughout the universe, as particles go through it, they experience resistance, and some particles experience more resistance and act like they're heavier, and other particles experience less resistance, like electrons, and act like they're lighter. And some particles, like photons, experience no resistance at all, and they remain massless and still travel at the speed of light. So all of the properties of matter that we see and measure and hold so dear to us are really an accident of the history of the universe. If the Higgs field hadn't relaxed into that configuration it now exists in throughout the universe, then we wouldn't be here. So the fundamental structure of the universe is not at all conducive to our existence. It's just an accident that the Higgs field formed and allowed matter to exist in the form in which we measure it.
And so if everything's expanding, does that mean it's going to get to a point where it's going to expand so much that it's going to actually affect the reality that we're in? Or is it going to be such a slow change that we don't even notice it?
It's going to keep on. As far as we can tell, the universe is expanding faster and faster, and it's not going to ever stop.
So is that ever going to affect reality? Like, how is there
anyone? Well, it will affect reality in the far future, in the sense that all the galaxies that we now see, except the ones we're bound to, our local supercluster galaxies, all of the other galaxies will disappear. They'll eventually be moving away from us faster than light. So in 2 trillion years, all the rest of the galaxies that we can now see in the universe will have disappeared. And beings that exist around stars in our own galaxy 2 trillion years from now will look out and think they live in a universe with a single galaxy, much like we thought we lived in 1925.
So I just thought of something. This is going to open up a whole new time, right? When we look out, we see the past. Is that true?
Well, we see things as they were in the past if they're far away. Look, I'm seeing you in the past right now.
Right.
It's taking some time for your signal to get to me.
Yeah.
But light travels so fast, and electric signals and wires and waves travel so fast that it looks like it's instantaneous. But my now is not your now. I just said now, but when I just said now, you heard it a little while after I said it.
So okay, so now you're looking. So when we first of all, let me ask you this: is time travel possible? Do you think it's possible? Is it like theoretically possible?
Well, I wrote about this a lot in the Physics of Star Trek, but the laws of physics do not forbid the possibility of time travel.
Wow!
But they also suggest that it's highly unlikely.
Yeah.
That in order to the general relativity allows for the possibility of time travel, but in order to do that, you have to create configurations of mass and energy that are strange beyond belief. And many physicists think there are probably laws of physics, of quantum mechanics, that say that you can't really create those conditions. So while time travel is theoretically not impossible, the kind of configurations you'd need to create a time machine are so extreme and weird that it's quite likely that they're not achievable. Can
you sort of theorize what that would entail, or no? Is that so?
Well, I read the Physics of Star Trek. I give an example of a wormhole. A wormhole, if it existed, which is a shortcut through space, would give if you could have a stable wormhole, you could build a time machine.
Have we ever discovered a wormhole? Is that even?
No, we don't know if they exist. In fact, again, stable wormholes don't exist unless you have exotic forms of energy that are totally different than anything we've ever seen or heard. But if you could create a wormhole of the type that Jodie Foster went through in Contact, then she could literally do she could come out the wormhole and come back and be younger than she was when she left.
Now, in the movie with McConaughey,
Yeah, Matthew McConaughey. Yeah,
what's that movie called?
Contact.
Yeah, no, I'm thinking of the one where he goes into a wormhole.
Oh, Interstellar.
Interstellar, yes, yeah.
Yeah, one of the worst movies ever made. Yeah.
Coming from a theoretical physicist, I should take your word for that. So that's completely nonsense. That couldn't even. They did no.
Well, some things are nonsense. My friend Kip Thorne, who later won the Nobel Prize, helped design the images of the black hole around the star, because that's kind of a fun thing to do. But most of the movie is just complete scientific nonsense.
Right. So a black hole is not the same thing as a wormhole.
Oh, absolutely not. Well, hold on.
Okay.
We don't know what happens at the center of a black hole. We don't know what happens at the singularity. Maybe it's a tunnel to another universe or another region of the universe. The only problem is you wouldn't survive the journey. So
yeah,
you'd be stretched into spaghetti and torn apart when you got close to the singularity by the tidal forces of gravity.
Now, I always thought about this because the black hole, it stretches you out, right? But if you were to get put back into the shape that you were in before you went into the black hole, would you theoretically be back to life again? Or is
you're asking me if I took apart your body into the individual atoms and I put them all together back in the same way, would you be you? And the answer is maybe, and that's the transporter.
There you go.
Star Trek. And we'd be great to do the experiment. The problem is the laws of quantum mechanics say that I can't really do that, because I can never know where every atom is in your body and what it's doing at precisely the same time, because of the laws of the Heisenberg uncertainty principle, and therefore I can make an approximation of you, but I'm not sure it would have the same memories or thoughts.
Yeah, because you hear about people talking about, like Elon Musk says this, like it might be possible one day to download your consciousness into a computer. It's like, okay, let's say I did that. Let's say this is all true, right? Mm-hmm. And I download my consciousness into a computer, but I still go on living. My physical body, I'm still alive. I go on living and I die. And I have no idea what my simulation version of me in the computer is doing. So is that even really pointless? Is there even a point to that?
Well,
or am I just giving life to
another? But your simulation feels like you. So I guess you can kind of feel like people constantly want remnants of themselves to persist past their death. And that's one way, I suppose. Another way is writing books, I guess. But
yeah.
And so I think that I don't know what people's motivations would be, but the idea is interesting because you can imagine lots of it's all science fiction, right? If I could download your consciousness, then if you got sick and maybe you could in some problem they could do something, and then maybe you could upload the consciousness back and be yourself again. All sorts of strange and possible things.
It makes you wonder. So if that's if that's possible, first of all,
it isn't possible now, but yeah,
right. If so, who would be there to monitor this computer with everyone in it? And then eventually, when people have to get off the planet, because climate change is inevitable, the world's not going to stay here forever. It's not going to. Eventually, we have to get off this planet. Then what? Do they take the computer with them,
why should they go? Just send the computer.
Right. There you go. There's a solution.
No, I'm serious. The only kind of interstellar travel that makes sense to me is to have microscopic robots that encode intelligence and if you wish, can build biological beings on the new planet. But I think the idea of sending 200 pounds of bags of water into space to colonize the universe seems ridiculous because we evolved to survive in this environment we're in now. We're not very good up there.
Yeah, and that's another question is like astronauts, when they go into space, it seems like they rapidly start to evolve and they start to lose their bone density and stuff like that.
Some things like bone density get smaller, although it's recovered quickly when they're back in the gravitational environment. And of course, unlike the protected environment around Earth, when you're in interplanetary space, you'll die from the radiation. So it's not a good place to be.
Yeah, and then back to time travel for a second. If time travel really was possible, I don't know. I mean, wouldn't someone already have came back by now? Or unless we're just the beginning, it just happened to be the beginning of everything.
when I talked about time travel, I used to have Stephen Hawking wrote the foreword for that book, the Physics of Star Trek, and he used to say time travel is impossible because if it were possible, we'd already be inundated by tourists from the future. And
Exactly.
as I like to say, I countered him by saying, no, they all went back to the 1960s and no one noticed.
That makes sense. That's great. Now, so now is time travel more possible one way than the other? Is it more
It's
possible?
definitely possible. We're doing it right now.
That's true. This video is going to be eternal. We're going to be
No,
eternally.
not eternal, but we're moving forward. I just went from the last second to this one. I have been time traveling the entire time you've
Oh,
been talking to me. I'm time traveling. I'm moving forward in time. So moving forward in time is incredibly easy.
yeah. What
You
about
just don't have
speeding
to
it up
do
though?
anything. So if you asked if it's easier in one direction than another, it's certainly a lot easier to move forward.
What
Backward
about,
is the problem.
what about moving forward faster?
You make time move faster. Well, you know what Einstein once said when explaining relativity. He said, if you're sitting on a hot stove, a second can seem like an hour. But if you're talking to an attractive woman, an hour can seem like a second.
There you go. That's a really good answer, actually. Is it?
It's Einstein's. You can thank him.
That's relativity right there,
Yeah.
right? So I had a question I was going to say. I forgot what it was though. But so yeah, okay. So let's say, let me ask you this: how long do you think this planet has left before we have to get off this planet?
I don't know. I mean, I know in the long term, I know that in 5 billion years, the sun will grow into a red giant, and the Earth will be inside the outside of the sun,
So we have
unless we move the Earth, which is possible.
really.
But yeah, sure, it's possible to move the Earth. So I know that's going to happen, and in about 5 billion years, also the Andromeda Galaxy will collide with the Milky Way galaxy. Now that won't cause as much. In general, it won't cause a lot of problems because stars are so far apart, you won't really notice anything. But the nature of our galaxy will change. But how long life on Earth? Well, in 2 billion years, there'll be a runaway greenhouse effect on Earth no matter what we do. Not the kind of greenhouse we see, but the kind of greenhouse that produced Venus, because the sun will be 15% hotter and water will begin to evaporate, and it's a big greenhouse of gas, and you'll eventually get the temperature of the Earth will be something like 1,000 degrees, something like the surface of Venus. So it won't be very hospitable then. So certainly in 2 to 5 billion years, the Earth is not going to be a place you want to be in, at least where it is. But beyond that, I don't know. And I always say I don't make predictions that are less than a few billion years in the future because first, no one will be around to check them, and secondly, it's a lot easier.
Well, we're in the age of video now. You might. I mean, you're an award-winning physicist. People might be looking you up in the year 5,000. I mean,
Yeah,
I'm less
maybe it's hard if they can figure out a way to run the software on a 5,000-year-old computer. Yeah, I guess so.
I thought about that. I'm like, okay, so the VHS and all that old technology doesn't really get transferred over, but sometimes it does. Only the good
stuff. It does if you're careful.
Yeah,
but you've got to remember. I mean, just think about in our own planet. I mean, how few things from 2,000 years ago have survived?
Right, very few compared to the grand scheme of everything. And it's always the most important things, very selective things. And
they're only important because we find them. They could just be a grocery list.
Yeah, and religious stuff.
If we find it,
right?
It tells us what they ate back then.
So, do you think it's more likely that the humans to survive would have to go onto a spaceship and just kind of float in space, or do you think they'd find another planet that's hospitable?
Well, there are lots of potential planets, and the question is getting from here to there is a hell of a hard job.
Right.
I think it'd be easier to consider if we needed to colonizing other parts of the solar system. But that's a lot. But the point is, it's not urgent. I mean, it's not urgent. We're talking billions of years in the future. But I mean, it's a good idea to not hedge your bets, right? There's going to be large asteroids that'll be hitting the Earth and other things over time. So it's not a bad idea to have other outposts of humanity if you want the human condition to continue to exist. I mean, it's better to hedge your bets in the long run, but it's not. We don't need to go to Mars next month.
Yeah, because the only reason I'm thinking about that because it's inevitable that's going to happen, and even if it's billions or millions, however many. I'm just throwing numbers out there. It's gonna that day will happen. I mean,
yeah, I think though. I mean, some humans will be on Mars. Absolutely, it just won't make much of a difference.
yeah. Do you think Mars is a good? Do you think Mars is hospitable? Like, what do
Well,
you do?
no, it's pretty inhospitable. No, I'd much rather be here.
Right,
It's
but
pretty.
can you change the atmosphere?
You could, yeah, you can imagine. Um, you can imagine it. Ways to make Mars more habitable. It's just probably a lot easier to make the Earth more habitable.
well, yeah, that obviously,
Yeah. So you could. So, but Mars right now, I mean, if you would die from radiation if you were on the surface of Mars for too long. Yeah. The Matt Damon movie was nice, and I liked I liked the book, but the radiation on the you die from 3 or 4 years sitting on the surface like he did.
yeah. The last thing I want to touch on is the idea of a center of the universe and there not being one. How do you explain that? There's not a center.
Well, I am the center of the universe.
Nice. Me too.
But the point is, we are all the center of the universe. We're all the center of our own universes. There is no center of the universe, just like there's no center of the surface of the Earth. Where's the center of the surface of the Earth?
I don't know.
Any place is as good as any other place.
North Pole? I don't know. What do you say?
Well, North Pole is nice, but or the South Pole or here.
Or what
they're
about
all the same on the surface of the sphere. Every point is the same. And in either a flat or open universe or a closed universe, the same thing is true. And it can expand just like a sphere can expand, but it doesn't mean that if I blow up a balloon and put dots on the surface of the balloon, every dot moves away from every other dot, but there's no center there. And that's a sort of a two-dimensional curved space analogy of a three-dimensional curved space in our universe.
So there's no like core to the universe. It's just
What do you mean core? It's three-dimensional and it's the same in all directions as far as we can tell, and it's just expanding.
so there is a core, right?
No.
No.
If because every point is moving away from every other point.
Okay.
And so there's no special place where it's not everything is moving away from one point. Everything is moving away from every point.
Yeah, I'm still trying to wrap my head around that. You got to remember.
Well, again, I hate promoting my books. I actually don't. But in Universe of Nothing, no. But in Universe of Nothing, I provide some pictures that make it easier to understand what's happening.
And that's exactly what I was going to say next. Is where can anybody look for some more work on you and your websites and whatnot?
Well, my website, there's my personal website, which is lawrencemkrauss.com. There's the Origins Project website, which is originsprojectfoundation.org, which has the foundation that I run, the podcast, a lot of other things. My personal website has things I've written about, and of course I tweet at Krauss1, wishing I didn't, but I do. And you can find me on Facebook, but there's lots of ways to find what I'm doing.
This has been fun, man, and I really hope we could do it again in the time traveling future.
Okay, good. Well, it was fun. It was nice. Thanks for connecting with me for this short time. And I guess I'll say that this hour passed like a second.
Yes. And everyone watching, you have just attained true gnosis. There you go.
You have just attained true gnosis. The demiurge has no power over